So let's calculate what is this integral. That is what we have to do. And well, if you followed statistics in the second semester, and if you work with the Gaussian distribution, it should be possible to do for everyone. It's a little bit tricky, but it is just the integration of a probability density function. Okay, let's do this. First step, variable transformation. I define that the variable xi, and I use now a new variable, is equal to 2 times set. Okay, let's substitute in here this. So what we get is then 4 set square. The 4 cancels with what is in the denominator, and then this integral from minus infinity to plus infinity turns into e minus set square, right? If we have 4 set square here, the 4 cancels, we have just minus set square. But take care, now here we have to integrate over d xi. Here, well, we need then d set. So let's do the derivative of my assumption. Well, that is d xi is equal to 2 times d set. So if I have xi here, for d xi, I can write down 2 times d set. Well, the 2 is a constant. Move it immediately in front of the integral. That is 2 times this integral. So what I'm asking you now, calculate the integral of this, right? The 2 we don't care for a second. So let's define that this integral we have to care about is called I, and it's the integral from minus infinity to plus infinity, and it's minus set square d set. That is what we have to do at the end. How can we do this? Well, first we square this whole guy. Yeah, we think about I square. Yeah, I square is this integral minus infinity plus infinity, and well, I can write it for a second like this. Yeah, this is the first times second. Yeah, if I square this, I make 2 times this integral. This. Okay? I square this. This is a kind of trick what we need. And now I can write, instead of set, I can substitute, I use 2 other letters. Yeah? I write a letter. I can say integration from minus infinity to y. Let's call it x squared dx times the same integral y squared dy. I just say here z is equal to x is equal to y. And in the first integral, I write it with the x letter, and the second with the y. Why not? Whenever you disagree, raise your hands. Yeah? Okay, well, this can be moved together and can be written as, so we do integration, double integration, from minus infinity to plus infinity over the exponential function x squared y squared dx dy, right? I just move the integral here, bring the exponents together, and I have then dx and dy here. That's a double integral over dx dy. Okay, now we have to do this. This is now a critical step, the next one. And I promise you, this is the only way to solve and to get an integral of this or this. There is no other way. Only this. So the next is, here I see something interesting. I have 2 variables squared. That what pops up when I see this is Pythagoras immediately. Yeah? That's the only thing I have in mind. And therefore, what I have to do at that point is I have to transform this integral into what we call polar coordinates. Polar coordinates, right? That's basic mathematics, high school. Transforming a function into polar coordinates. That's what I did, up and down it up. And so, what does this mean? Okay, can I give you a reminder? So we have here x and y on my axis. And now, the polar coordinates is plotting this coordination system onto a unit circle. Yeah, there's a slope 1 and there's a circle. Yeah, in a sense. Yeah, so. And the radius, as you can see, of this circle is 1. So now let's plot here a line. And we know that this is the radius, and this radius, yeah, r, is 1. So here we have a distance. Let's call it x, and a distance y. This is a rectangular triangle. X squared times y squared is r squared, Pythagoras, right? That is what when I see this, then I say immediately, if I take a closer look to this integral, minus infinity plus infinity, minus infinity plus infinity, this is the exponent minus r squared, right? Because this squared times this squared is this squared, Pythagoras. But if I have now here r squared, I cannot integrate, obviously, over dx dy, right? I have to find the correspondence for dx dy. And that is what we mean by transforming into polar coordinates. Okay. So this is my x, right? The whole distance. Suppose we increase this distance by a unit dx, yeah? A little bit. Yeah? So I increase x a little bit. And then, obviously, when I increase x a little bit, I will also change my dy. Yeah? So I have here, you can say, dx, and then I have here a dy, which is then modeling this change, the effect that has here. And so if I change dx dy, I get an area here. Yeah? And now I want to find another way to express this area. This area can be also characterized because we have here an angle, let's call it theta. And this, we have this sine and cosine. You know, the sine of theta, what is the sine of theta? It is y over r. No, that is this tangent, y over x. Sine is y, that's in the opposite direction of the angle, y over r. This is y. So this can, in other words, y, yeah, can be written as, this is r times sine of theta. Okay. And now the argument is the following. If I change x a little bit, this is the same then changing r a little bit, yeah? So changing the dr a little bit. So in a sense, dr and dx is the same. And then we are interested what happens with dy. So dy from this equation is r times derivative of this in respect of theta is the cosine. Well, this is, you know, that's basic, therefore I'm fast. And then we have here the change of theta. The cosine, if the theta is very small, is 1. Yeah? The cosine at 0, if the theta is small, is 1. So what we can say and see from here, my dy can be written as r times d theta. D theta. This length is this dy. Yeah, for this dy, I can write r d theta. Instead of dy, yeah, I can rewrite dy r d theta, because the cosine for theta almost 0, very small, is 1. And yeah, that gives me the change in respect here of dx, or in my case, if I change dr. So dx and dr, yeah, instead of dx, I can write dr. Now I have transformed this integral into polar coordinates. Here I have the radius squared, and for dx, we have the change in the radius, dr, right? Here's my radius, yeah? And for dy, I can write the y variable is r times the change in the angle theta. That's the transformation of this integral into polar coordinates. Well, the integration is then not from infinity, from minus infinity to infinity. Why? Because my radius starts here in 0 and can go to infinity. That's possible. And my theta integration, because it can go once in a circle, it starts also in 0, so no theta. And when it goes once, 360 degrees, that is 2 pi. It goes up to 2 pi. This integral is the same as this integral, just in polar coordinates. I do this because I can solve this, and you can't solve this on the right-hand side. Yeah? Here you can work for your lifetime until you are dead, and you will never find a solution, an explicit one. Here you will see one. Well, let's do this. I will do the following. I will first do the integration for r, and in a second step for d theta. So I separate this logically in the following sense. So we integrate the first integral from 0 to 2 pi, then we make a bracket. Then we write inside the bracket the inside integral from 0 to infinity, e minus r squared times r. That is the integral of dr. If we did this integral, we get a solution, yeah? And that solution is then integrated for d theta. First, we have now to find the inside integral, and then we do the outside integral. Okay, so outside, we just write it, but we have to care first about the inside. Okay, take a look to the inside integral. What we need to do this integral, we need a variable transformation again. Here the variable transformation I suggest is the following. Well, let's think about. Why not assuming that u is equal to 2r? Well, I have to think about. Yeah? If no, that's not a good guess. U is equal to r. I think that's a good guess. Let's see about this. What do we have then here? Well, then we have here, well, the integral is from 0 to infinity. Then we have here, if I plug in for ru, we get here e to the power of minus u squared. Right? So, now we have to, wait a second. If we calculate the derivative, no, it's not my preferred guess. This is my preferred guess. u is equal to r squared. I think that works out. Then, for r squared, I write u. That gives me e to the exponent minus u. If I do the derivative, I have du, and here I have 2 times r dr. So instead of r, I write now, bring this 2 over r here. So then I have, well, I have here an r, right? This r times r. And then for dr, I write du 2 over r. Then this r, and that was my intention, cancels out. And here I have 1 over 2, and I can bring the 1 over 2 outside all the integrals. That's a constant. And then what I have to do is just this integral, e to the power of minus u in respect of du. That's, once again, very basic. So what we have now in front, we have the 1 over 2 from 0 to 2 pi. Then my integral d theta. What is the integral of the function e to the power of minus u? Well, let's think about, is it this? If we calculate the derivative of this, we have this function, and then the derivative of the exponent in respect of u is minus. Well, no, we don't need the minus here. Yeah, we need the minus, right? Because we have this, and the derivative is minus 1, right? And then with this minus, we get a plus, and here we have the plus. We need the minus, yeah. And we have to do this integral. What are the limits? From 0 to infinity. So if we substitute the limits in my function, the first element for infinity, it's 0, right? Because this is minus, so its denominator gets large, so the term gets 0. And then we have minus, at, when we plug in here 0, it's 1. So what we have here, this integral, is 1. And now we continue. So what we have now, in front we have the 1 over 2. Then we have the integral from 0 to 2 pi. Inside here we got, this is minus, and now we have to do the integration for theta, right? This is what we, maybe I make here this bracket to indicate that was the integral we did, the inside integral. And now we have to do the outside integral over theta. Well, what is this? Can you tell me this integral over theta? It's just theta at my, well, 1 over 2, right? Don't forget what is in front. And then it's theta at my boundaries, 2 from 0 to 2 pi. And what is this? Well, if I plug in 2 pi here, the 2 cancels, we got pi. And if I plug in 0, well, that's 0. So this integral is pi. But what is what we computed? This is my I squared, right? We called this I squared, and then we moved on here. So we find that I squared is pi. We are interested not in I squared, we are interested in I. But this is easy. Well, if I squared is pi, then this is square root of pi. I think that was the homework. Yeah, basic statistics, how to handle Gaussian density and do integration. Okay. Sorry?
To raise it, to square it, that was the only principle. We have to do I squared.
Maybe. I can't remember everything, but yeah. So what we got is that this is I, right? And here from our variable transformation, coming from here, from our fundamental solution, we see we have to care about the 2. So what we have is that the fundamental solution, if we do this integration, we get 2 square root of pi